All right, good morning. I did post just a little change to program assignment 4. But as I said, if you've done it already, don't worry. You can submit anything. Remember, you're asked to implement the backward Euler method, and it turns out you have to do Newton for that, so that's most of the difficulty here. If this was forward Euler, you would already have done it from day one. We talked about differential equations. So the difficulty here is this Newton method. And it's not that hard, I think, but I know that it will confuse some of you because it's mostly notation. So see how that goes. The thing here is that, as we all know, we talked about 5.11. This is an exercise in 5.11 where we talked about stability regions for Runge-Kutta. And I told you a number here. This is the right version. That number is correct. I wrote 2 squared of 2 there. But if you already did it with that, keep on going. It's not a big difference. But I mixed it up. If you remember the Runge-Kutta stability region, I had a MATLAB script that plotted it, and it looked like this. Okay? And you're interested in this number here, which is that number, minus 2.78, 53. What I mixed it up with was this number, which is sometimes very important, which is 2 squared of 2. So this is the right now. They're very close, but it's slightly different. You get a slightly different big N. But the whole 10% thing worked out such that it didn't really matter with this error. That's the reason I didn't discover it when I made the error, because 10% is so much that it compensates for that error. But you know, it should be correct, and this is correct. So the idea is that you find the h. Remember, you will find a bound on how small h has to be, on how large h can be, by making sure that h lambda is inside this region. Any questions on the programming assignment? How are you guys doing? It's due in a week, right? So not today. But you should probably start this week. If you get it right, this is, as the other ones, really short. I hope you read my solution. I posted the solution. Please read the solutions. Even if you did it and you got it right, maybe I implement it in different ways and you can learn something from it. But it's kind of nice. I try to make these not a lot of coding when you get it right. It's really just not long MATLAB functions at all. And this is also straightforward. I know from Piazza that people are kind of getting the expected results from B here, I think. Namely, I don't know. I haven't really heard about experiences with backward Euler yet. Maybe people are struggling with that. Anyway, well, I'm bringing it up again on Thursday when more of you have got a chance to look at it. We are now in the last week of new material. So that's something to celebrate, maybe. There we go. We're going to do this. You have, of course, homework due next week on Tuesday on this new material, all the way up to 6.6. Did I even have homework on that? Yes, 2 problems. So this week will be, of course, you might want to read ahead a little bit. You know, I usually try to be a week ahead, but I can't do that now. Next week, I don't know what to do, or I know what to do. I'm going to just review stuff, but I have 2 lectures for it. The main reason is that I can't cover new material because I wouldn't have time to have homework and quiz on it, right? So I was thinking do a review similar to what we did last time, but then maybe also go through all the MATLAB functions and review those. But if you have comments on what to review, that would be nice too. And in time for these reviews, I will post a lot of old final exams just to know exactly how to prepare and practice. But anyway, we are doing chapter 6, which is about direct methods. We talked about Gaussian elimination, which you already know. We did a bunch of examples. I think the big thing there was operation count, which is annoying, but actually quite straightforward. In just terms of study advice, it's one of those things that is new to numerical analysis, and it's fairly easy to ask about. So I think you'll see in the old exams that it's something that usually shows up. So you know, don't make the mistake. It's an easy thing, so don't miss on this one. Maybe here's a big numerical analysis thing that you gotta really do. In our small examples, it doesn't matter, but in a real code, you have to do what's called partial pivoting, which means that when you do Gaussian elimination on a matrix like this, you know from Math 54 that you can just keep on going and everything is fine. You can just subtract 3 times that row from that row and everything is fine. And of course, it will be fine in the computer as well. But in general, it will not. It's actually a little counterintuitive. If that was a 0, Math 54 would tell you it really doesn't work, and the fix is easy. You flip them, right? But in numerical analysis, it turns out if you have a 1,000 by 1,000 matrix, even if this is not 0, as you keep on doing it, small round errors will go really bad. I had a little 2x2 example that showed that. But what you do is that you always make sure that this guy is the largest possible. So you flip, even if this is not 0, to bring the 3 up there. Okay? So numerically, that's what you always do. It's called partial pivoting. Very simple. You find a row. You're about to do step. I mean, this is, of course, pivot 1, right? And you look below it, and you find the largest and flip those rows. That's what you have to do in practice. That's partial pivoting. I talked about scale pivoting, which is the same thing, but looking at the magnitude of numbers. So basically, if I put 30 and 40 there, it would find a scaling factor that is actually 40 in this case, but order 10, and it would scale correspondingly. But it would still flip the rows. It wouldn't change that fact in this case. We had the computer code. I advise you to look through it, Gauss elim, whether the one we did or not. And maybe this is a little cryptic MATLAB for you, but you should be able to figure out, at least, based on the comment, what it's doing. Namely, find the largest element below the pivot, including the pivot itself, because it might be that this is the largest, right? So you might want to do that. And then these rows actually do the flipping of the rows, these lines of code. This here we went through. I did mention that you all know how to do it since high school, but you should think about, if you're new to programming, really go through every little detail and see how these numbers show up. It's a great exercise in writing things in MATLAB code. Same thing with the back substitution. These, of course, also led to those operation counts that we discussed. Just figuring out, here's a multiplication. How many times is it performed? Well, clearly just once on that row, right? But that row is executed n minus I times, which is tricky because I changes. So it actually changes. You have this j going from I plus 1 to n. That's n minus 1 I times. And there's an outer loop here. How on earth can you count the number of multiplications? Well, the idea was that you write the sum from 1 to n minus 1. And you observe that for any I, this is going to be n minus I times. And this is going to be n minus I plus 1 times. So really, for each I, you're doing n minus I times n minus I plus 1. And then you could simplify it and get it out. So these are the type of exercises we did. Then I talked about 6.3, which is a little iffy to teach because it's just, I don't know. Is it completely trivial for you guys? Or do you need a review on it? It's part of the course. If you've taken 110, it is completely trivial. It should be. I know some of you have not taken 110. So if it's easy for you, just, congratulations. It makes life easier. And the next chapter that I'll discuss quickly today, Determinant, is, of course, as trivial. But let's just do it anyway. We defined equality. This was almost too easy. A bunch of easy properties regarding scalar multiplication and addition and subtraction. Then, of course, we just defined multiplication, which you also know what it is. Many ways to see it. Here we emphasize that it's a series of dot products. That's, of course, the way you do it when you do it by hand. But any good linear algebra book should have taught you that it should really be seen as A times each column of B. Because A is a linear operator operating on each column of B. It depends on what you want to use it for. But if you want to understand matrix multiplication, these dot products are not that helpful. But it's, of course, the definition we used in many of the proofs, namely that it's quite easy to just write down. And, of course, the inner dimensions must match. Special matrices, square, diagonal, identity matrices. These might be new to you guys, upper triangular, lower triangular, but they are completely self-describing. Just for other references, this includes the non-zeros on the diagonal. Okay? So it's really just 0 below, so this would be an upper triangular matrix because it's OK to be non-zero on the diagonal and above. Okay? The transpose is a lower triangular matrix. If you put all the zeros, if all the diagonals also to 0, we call it strictly upper triangular. But it's not defined here. Matrix multiplication has some interesting properties, and maybe one of the first things you should observe, it's not here, is that it does not commute necessarily. Okay? In fact, AB might be defined and BA might not be defined if the inner dimensions don't match. Even if they do match, even if everything is n by n matrices, they might not be equal. So that's the first thing you learn. However, they are associative in this sense. A fun little exercise in computer science is to figure out what is the best way to evaluate A times B times C. It can make a huge difference depending on those inner dimensions. And it's actually a problem that you can solve, I think we dynamic program. I should give you an example, but imagine, for example, that b times c reduces to just a scalar. It could be a dot product, right? A row vector times a column vector. Then it might be a good idea to do that first, and then a times that, etc. So it matters which order you're doing. This was easier. We didn't even prove that. Identity multiplying a matrix is also very easy. And scalar multiplication is also very easy, I think. So the only one we focused on was number A there. And the way you do these proofs is just turn the crank proofs. Plug in the definitions. Maybe start on both sides and try to make them equal. Or if you know what you're doing, start on one and simplify it to become the other one. Then we talked about inversion. Don't ever talk about an inverse of a non-square matrix. It's not defined. Even if it is square, it might not have an inverse. And if it does have an inverse, we call it A inverse. Otherwise, it's singular or non-invertible. This is unique. We showed easily by assuming we have two different ones, and just a few simple operations shows that they must be equal. Do it twice, and you get back to where you started. You just look at it, and you observe this. I know you take it for granted, but that's not a proof. But this is easy to see. And of course, here comes maybe something we had to look at more carefully, namely that when you do a product and then an inverse, you can distribute the inverse on each of the matrices, but you have to flip the order. And there are many ways to convince yourself of that. But I mentioned that many of these proofs are of the form that I'm proposing an inverse. Proving something, if I propose an inverse to you and you want to prove it, it's usually just plug it in. And at the end, we actually use the uniqueness to say that this is the inverse, not just this is an inverse. But if you look at B and C here, I'm proposing inverses to you. To prove it, just take that proposed inverse and multiply it with what it's proposed to be an inverse of. And if you get identity out, you're done. That's how we proved C here, for example. Transposes, you all know what that is too. You change the dimensions in general. Trivial, maybe not completely trivial, but we could easily get it out by, again, just flipping indices. So again, when you go, proofs here, when you go into notation of sum and you do Aij, a transpose is so nice because Aij just becomes Aji, right? And you just flip, and then you can go back and forth as much as you wish. And something you use a lot is the last one here. This is also of the easy character that it's actually proposing an inverse. It's telling you that this left-hand side here is the inverse of A transpose. To prove that, you take this left-hand side and multiply it by A transpose and simplify and show that it's I. Then you show that you have an inverse, and the uniqueness from before says that is the inverse. Quite straightforward. This is so commonly used, since this is the case, we often are, I don't know if you've seen that in linear algebra, but we write A to the minus t. We can combine them because the order doesn't matter. It's a little ugly in a way. I mean, it's not minus. You realize that t is a special symbol, right? I mean, A to the minus 2 is something else, right? That is the inverse of the square or something. But minus t is just a symbol. So maybe I shouldn't promote that. Anyway, I thought this was much review. Look through it if it wasn't. Even more review is going to be this, but let's do it anyway. This is 6.4, determinants. All right. What can we say about determinants? There are different ways to define a determinant. Sometimes it's defined recursively. I think this is one of the most common ones, to define it in terms of, I think a common way is to define permutations. And you end up having a definition saying that the determinant is the product of all types of permutations of how you can pick. So basically, if you have a matrix like this, you want to multiply an element from each row, or column, but let's say row, and you got to not choose the same column twice, right? So there are only two variants here. You can take this guy times that. You can take that guy times that, right? And there's something called a parity of a permutation. So namely how many times you have to flip to get from the identity permutation to that permutation, which shows that if it's odd, it should be a negative sign. So using this formula, you would figure out that that times that with a plus sign minus that times that is the determinant of this matrix. And this generalizes to any, but it's not a very practical definition. But it doesn't matter, it's just a definition. That the determinant of this guy, you got to consider all possible ways to pick one guy here, one guy there, and never the same, right? And you multiply them together, and possibly with a minus sign. About half of them have the minus sign, and exactly half of them. And that's the definition of the determinant. But more practically, I think, is to use this expansion by row. And you could, of course, also prove this from that or the other way around. Let's go slowly. First of all, a scalar has determinant, the scalar itself. Just one obvious warning here is that we often write determinants with absolute value signs, right? So determinant of A, I can almost recommend doing determinants instead of that. But when we have an actual matrix, it's kind of nice to put the absolute value. But the determinant of A, sometimes we write it as that, right? And that's completely ambiguous, especially when A is a 1-by-1 matrix. Because now it collides with the absolute value sign, right? So if anything, maybe make it a matrix like that. Okay? And why is it confusing? Is it inconsistent with the absolute value? It is inconsistent with the absolute value. It's almost not, because if it's positive, it's the same, right? The determinant of a scalar is the scalar itself. So it might be the same, but it could be negative, for example. So don't think of it as an absolute value. Anyway, here's how we just define them in general. We define a minor by cutting off I comma j. You tell me in I comma j, I can define this mij by taking out the row and the column ij. And then I get a smaller matrix. Multiply this by an appropriate sign, we get what we call a cofactor, which is really just negating if I plus j is odd. And then you can define the determinant by expanding along a row, or by expanding along a column. All right? So the typical special cases of that, or the simple cases, is that if you have a 2-by-2, you get. All right, we expand along the first row. So this definition here is, by the way, you have to keep track of what's going on here. I here is arbitrary, right? You can choose whatever row you want. J is not arbitrary, it's a sum over that. But you can choose whatever I want. Usually you do the first one, but suppose there's a lot of zeros along a row. That's a good row to do expand, just for hand calculations. Similarly, down here, you loop over the rows, but the j's are arbitrary. So to use this first definition here, we choose I equals 1, the first row, and then this formula tells us that we're supposed to do -1 to the 1 plus 1, or you just remember the checkerboard pattern started with a plus sign here. Okay? And then you get times A, which is that number there, and then you have to cut out these guys, and you get this cofactor, or sorry, you get the minor, because the sign is already there, which in this case is just D, because that's the determinant of the scalar, right? And then you're getting plus, and now it's minus. Now you do this guy, then you're getting -1 to the 1 plus 2 times this guy times this smaller minor, which is, again, just C because it's a scalar, right? So this gives you the familiar AD minus BC. And that's so small and boring, so let's just immediately do the 3-by-3, and then we're done. But this one you might want to remember by heart, that if you have a 3-by-3, what do I call these things? A, B, C, D, E, F, G, H, I. If you expand along the first row, for example, you are going to get. And I'm going to do the signs. You can have this little memorization if you want to, but this is what it's going to be for the simple reason that it's -1 to the I plus j. And that gives you this pattern. So it's going to be plus. Let me put the plus to be extra careful. That guy there, A, times the determinant of this 2-by-2. And let's write determinant of EF HI. And then you get a minus sign, because this B, and now it's determinant of cutting out that guy and that guy. You get DFGI, FGI, and now it's plus C times determinant of DEGH. And when you simplify all this, you're getting A, E, F. Let me write it with all the plus signs first. Not F. A, E, I. I'm going to do all the plus signs. Plus B, F, G, plus C, D, H. And then we do all the minus signs. A, F, H, B, D, I, C, E, G. OK? And I actually, so that you could do. I usually remember this one in the form of you go always down like that. So that's one term. Then you go down and you wrap around. Then you go down and wrap around even earlier. Okay? These are positive signs. Then you do the opposite. You go to the left instead. The first one will be that with a minus sign. Now it gets messy. dash with a minus sign. That's how I remember it. Anyway, whatever way you want to have it. Let me just warn you, if you do remember it like that, when you go to a 4x4, which I'm not going to do, I'm sure I could trick you, if you haven't seen this before, based on the pattern that this was AD times AD minus BC, and this was AI BFGC minus those, right? I'm sure I could trick you guys into the fact that this would only be 8 terms. Namely, you do the same pattern, right? Certainly looks like it. And then you do the left, right? Well, that's wrong. There are 24 terms. So it gets determinants explode in terms of computing them. A little bit of numerical thing here. I know determinants look really cool in linear algebra. It's almost worthless in numerical analysis. It's used for theory only. We just don't compute determinants. There are so many things bad about them. One is that they're expensive to compute, but we'll show you how you can do it, like solving a linear system. But let me first tell you, why would you want a determinant? Almost one of the main reasons we do, and it's coming up soon, is that we want to figure out if things are singular or not, right? If things are 0, if the determinant is 0, the matrix is singular. So numerically, you would probably say, what? If it's small, then it's singular? Yeah, maybe, right? So, it's never going to be exactly 0. Then how about the matrix? You take the n by n identity matrix. It's not singular, right? Then you scale it by a small number epsilon. That's, well, it's certainly not a singular matrix. I mean, mathematically it's not. It's a determinant. But it's also an extremely well-behaved matrix. It's trivial to solve. You just divide the right-hand side by epsilon. I just scaled everything, right? But the determinant of this is what? Epsilon to the n, right? So, just put epsilon equals 0.1 and make it 1,000 by 1,000, and your computer, it's the crazily smallest number you've ever seen. So it's really, really close to 0, and yet the matrix is great. So determinants do not tell you. A determinant being 0 tells you that the matrix is singular. A determinant being really close to 0 doesn't quite tell you anything. In fact, we have another concept called condition number for this, but that's beyond this course. Anyway, a bunch of properties of determinants that are kind of nice to know, and I think you've seen them all. Make zeros anywhere, and you get a 0 determinant. You notice that this interpretation tells you that that must be, well, both of them are easy to see. This one tells you that you will always multiply by at least a 0. While this interpretation, again, tells you that if you have a row of zeros, you can choose that row as your expansion. And that will also give you all zeros, right? So that's easy to see. 2 rows or 2 columns equal, it's actually, so that's more interesting. You might want to see determinants as the volume, especially in 2D and 3D. You can see the volume of the in 2D, this parallelepiped that it spans, right? The 2 vectors here. And if 2 are equal, the volume goes to 0. Maybe it's easier to see that if we look at property E first, we can see B easier. You can switch rows, and determinant does not stay the same. It changes sign. And again, the volume interpretation gives you that too. You multiply one row by lambda, the determinant multiplies by lambda. And in particular, that means that if you multiply all the rows by epsilon, you get a lot of factors of epsilons coming out, right? So it's a very easy mistake to think the epsilon pops out. Here's the E I talked about. You can add a multiple of another row, and it does not change the determinant. Okay? So that gives you property B from A, because if you have B, you could, of course, just subtract the 2 rows, and you get a 0 row. Product, determinant of a product is the product of the determinants. Transpose or not does not matter. That's pretty cool. That's pretty cool, clear, I think, that all these determinants don't care about the transpose. Every time I say expanding by row, you can replace it by expanding by columns, etc., and this motivates that. This is trivial to show by just writing determinant of A times A inverse, using this property. And of course, it's equal to 1 because it's the determinant of the identity matrix. And the final property is that if you have a bunch of zeros on this special matrix, if you have zeros here, the only, and again, I kind of like this interpretation good here, though. The only way you can pick one guy from each row without picking a 0 is if you pick the 5 diagonal elements, right? And it's going to be a plus sign. So the determinant of an upper or lower triangular matrix is just a product of those diagonals. And in fact, this is how you compute, this is how you calculate determinants in practice. This here, you can actually talk about this, I don't know if you see, so 2 terms, 6 terms, 24 terms. How do they scale? Sounds like factorials, right? And you can convince yourself of that easily from the definition. How did Gaussian elimination scale? That was the point about the operation count, right? That I mean, there wasn't 2/3, but it was n cubed. So what's worse, n cubed or n factorial? I think you might rather do these 6 terms than doing Gaussian elimination on a 3×3. Because the Gaussian elimination had a lot of division and stuff. But a computer doesn't really care. But it could be argued that for a 3×3, computing a determinant is easier. 4×4, even if there are 24 terms, I don't think you'll be too happy doing Gaussian elimination on this one either. But how about n equals 10? Then Gaussian elimination is about 10 to the 3, 1,000 operations, right? While 10 factorial is millions, right? So, and make it bigger. Factorials just explode. So the properties you use to calculate determinants is really just property E and property I. In the sense that E, you should recognize from our Gaussian elimination before. When you do Gaussian elimination, unless you flip rows, you can flip rows if you want to, but let's say we don't, then the determinant stays the same. And remember, the goal of Gaussian elimination was to turn the matrix into an upper triangular, right? So the way we compute these things is really to say, here's an example, 1, 2, 0, 2, 3, 1, minus 1, 1, 1. The 3×3 doesn't explain quite the benefits, but if you do Gaussian elimination, you subtract 2 times that, you get a 0, minus 3, minus 1. You subtract 3 times that, you get a 0, minus 5, 1. And then you do another step of Gaussian elimination. Then you get 0, minus 3, minus 1, 0. You subtract what? 5/3 times this row, right? That's the multiplier from this row. To put a 0 there and getting 1 minus, well, the multiplier was 5/3, but then it says minus 1 there. So I would say this is equal to 8/3. Okay, all of this was one entry. All right, and that gives you immediately the determinant. If this was A, that gives you the determinant of A by rule number. So let's see. Rule number E told me that everything I did here did not change the determinant. So this determinant is the same as that determinant, right? And property I tells me that this determinant is 1 times minus 3 times 8/3 equals minus 6. So that's how we calculate the determinant. What if I put a 0 there? I mean, you could, of course, just do this differently and get away with it. But suppose you want to do exactly the upper triangle like we said. Then you want to switch rows. It's all good, because we have a property named C, which tells you that minus signs will pop up if you do. Might pop up. But you could do that. All right. We got to have this anytime we teach linear algebra and determinants and everything, right? Often referred to as the fundamental theorem of linear algebra. And it's described differently and different. I think when I teach it, it has 8. I mean, there are so many ways you can formulate this. But you know the story. It's various ways to talk about the matrix being non-singular. One is that the determinant is not 0. The other one is that the inverse exists. You also know that it means that you have a unique solution to AX equals B. These are square matrices. You also know that AX equals 0 doesn't have any spurious modes that can fly around and still produce a 0. It can have only the trivial solution 0. And by the way, A and B go together fairly trivially. I think maybe what's new now for this course is E. I don't know if you've seen that. A Gaussian elimination is going to work provided you do flips of the rows. That can actually quite easily be shown that if Gaussian elimination breaks, what is the only way Gaussian elimination can break down? If I have a 0 there, it would break down without row exchanges, right? But this is including row exchanges, so then I flip. So what's the only way it can break down? All of these are 0 at some point in the process. So it's not like you just look at the matrix. You have to do it, and you have to finally end up with a whole row of pivots that are 0. And then you can easily show that then you have a subdeterminant here that is 0. It comes out pretty easily. But it's, of course, nice to know. In fact, many times, just figuring out if a matrix is singular in practice is the same thing as just doing Gaussian elimination. And if it doesn't work, it was singular, right? That's really, in linear algebra, we're often like, oh, first we look at the determinant, because it's so easy to compute, right? But it's not. But we think for our small example. We look at the determinant, we see that it's non-zero, then we say, oh, well, now we do all the work of a Gaussian elimination. In the real world, it's really the other way around. Gaussian elimination is the cheapest way to compute the determinant, even to determine if it's 0. And you just do Gaussian elimination, and if it works, it worked, and you're done. That's all I wanted to say about determinants for now. So how do you think MATLAB does it? Determinant of a random matrix, and then we tick-tock it. All right? Well, the fact that that went so fast, so again, here you see the problem with, you should probably redo that one. There's some caching effects. So the timing things is difficult. Anyway, this looks pretty consistent. And then we make it 10 times bigger. And this number went up by something that I was hoping to be a factor of about 1,000, but it's not because it's so small. It's similar to the stuff I did before. Maybe this should go up by a factor of 8, but it's not. There are caching effects. This is as bad as the demo I tried to make with the operation counts before. But they're definitely doing it by doing Gaussian elimination of some form. Maybe they're smart in some way, figuring out that they don't need all the numbers or something, because after all, they just want the diagonals at the end. But essentially, it's Gaussian elimination. You can immediately tell that it's not the definition, because factorial of, as I said, 10 is a big number. But if you make it twice as big, this becomes 10 to the 12 bigger, right? I mean, while clearly our little demo here showed that it doesn't scale that bad. All right, now comes a pretty cool thing that you, actually I think some people teach it in 110, but it's not typically taught, definitely, sometimes, I'm not sure. It's the idea that we don't really do inverses. We train you to think that inverses are great because you can compute them and then solve linear systems. But we don't really do it. That's just confusing. But yeah, I can keep that there. Don't get confused by that. Here's what it's going to come to at the end. Gaussian elimination. For now, without pivoting, and we do pivoting later, can be written as that you have a matrix A, and it's anything. Let's say it's, well, by anything, I mean no special properties. OK? So Gaussian elimination, another way to express it is to say that you can factorize, or you can compose this. So it's called a factorization. In the sense, for the same reason that you can factor a polynomial. If you break something apart into a product, we call it factorization, right? I'm going to take A and break it apart as a product, of course, a matrix-matrix product, between something I call L and U. And not a big surprise is that this U is exactly the end result if you don't pivot. It's an upper triangular matrix. It's a good name. 0 is all down here. What's not so clear is that this L is lower triangular, and it has 1s here. It's lower triangular, and it has whatever here. All right? Probably the most important and famous matrix factorization method. It's called the LU factorization for obvious reasons. And Well, what we're going to look at is to see that this can be done. Let me start by saying why it's useful. There are many ways it's useful for, but one obvious one is for solving AX equals B. So suppose you do this factorization, and it's not, I mean, you're not going to be super impressed. I'm not going to tell you that you can do Gaussian elimination 100 times better. This is We're going to do Gaussian elimination to do this. But there will be some subtle, important differences here. But suppose you have done this, and you want to solve AX equals B. Then it's pretty straightforward. Of course, this is the same thing as solving now LUX equals B, right? And because I just say AX equal to L times U. And if you look at this, you should immediately say, hey, this is going to be quite easy. Because you're going to just kind of invert one matrix at a time. By the way, we don't use inverses, but I use the terminology that if you want to solve for x here, you should be much happier about that than this. Why? Because this is a lower triangular and an upper triangular. You just get the back substitution, but there's also a forward substitution. So these are the steps. You set y is equal to ux. So basically, first you're trying to solve for that. And that's, of course, Ly equals B, right? Is that easy? Well, just like solving a system U something equals B is trivial because it's just a back substitution, right? I know in terms of MATLAB code it looked like the second half, it looked like not what is the fundamental difference, but we did the operation count. And I think you all know that the back substitution is a whole order of n faster. It's easy to solve a triangular system. You just start at the bottom and go up. At the same thing, if it's lower triangular, of course you have to start at the top. So if I want to solve L times something equals something, this number, the first number is given by just dividing by 1. It just comes naturally. Then you subtract and divide by 1, etc., right? So solving Ly equals B is easy. Easy. It's only a back solve. All right, and then you do it again with U. So now you get this. You want the x at the end, right? And again, you have U is upper triangular. So this means that it's again a back solve only. All right? So what's good about it? Well, I haven't really told you how to make the A equals LU, but let's just say for now that this is useful if solving many systems. Suppose you have AX equals B1, AX2 equals B2, involving the same matrix. With the same matrix. Okay, why is that useful? Because whatever cost you pay, you do this once. And this is by far the most expensive part. And then each of the new B's, you can do this on. Remember the way we learned Gaussian elimination so far is that you augment the matrix by the right-hand side vector. You do it kind of together. And you forget what you did. Every time you multiply on a row, you do a row operation, you do it on B as well, right? It's not clear how to reuse. If I give you another B after you solve one of those problems that we did before, what we do here? Well, I don't have anything. But the way we described it here was that we augmented it and did B. It's not clear for you how to, if I give you another B after you've done it, to quickly solve AX equals B for that B, right? And I think many of you will think, but that's what an inverse does, because that's how it's taught in linear algebra classes. That you pre-compute the inverse, and every time you need to solve a system, you just multiply by the inverse. And this is achieving the same thing without using inverses, because inverses are horrible things. Extremely ill-conditioned, big numbers, loose sparsity pattern. We just don't want inverses. So in terms of this benefit here, you are probably used to this benefit from inverses, and now I'm telling you, you cannot use inverses in the real life. You do this instead. That's about it. There are many other properties. Of course, you can get determinants and stuff out of this. But for now, this is the motivation. But you got to probably just trust me when I say that this is useful. And we'll see why this is the case. How can this be the case? I told you that A, you can do Gaussian elimination on A. It is Gaussian elimination. In many ways, LU is the beautiful matrix way to describe Gaussian elimination. We used to describe it by row operations, etc. This is the way to describe it. And if you think about it, I said you take A, and you do all these operations, and it becomes U, right? So it sounds like, just looking at this, that all of those operations I talked about can be represented by a left multiplication of some matrix L. That's all it comes down to. So it turns out all those row operations, subtracting a multiple of a row from another one, is actually just matrix-matrix multiplication. And it has this nice structure. So let me show it with an example before we do the general case. So I'm going to do a 3 by 3, probably the same as before. No, it's a new one. So here's my matrix A. 1, 2, 3. I don't have a lot of imagination for my numbers here. That's my matrix A. And if you don't mind, I'm going to just introduce some terminology. Terminology is usually a killer. It just comes to a point when people know it gets confusing because of the terminology. We're going to have to put, to make it a little consistent, we're going to have to put these superscripts on A. Because remember, Gaussian elimination, we mess with A. We change it, right? So just for the notation to make sense, let's call them something. So this is the first A. What is the first step you do in Gaussian elimination? Without pivoting. Well, you want to subtract. I'm actually going to 2 on the fly here. Bear with me on this. But what you basically want to do is that, suppose I put an identity matrix here. Then, of course, I get the same matrix back, right? And I'm not going to write it. But if I don't do anything now, I get the same matrix back. That's not a very insightful comment. Now, suppose that I don't want the same matrix. I want the same matrix, but I want to subtract 2 times this row from this row. That's Gaussian elimination, right? Can you see that subtracting, you got to remember your matrix multiplication for this, and especially the various interpretations. Can you all see that if I put a -2 here, then this up here will still be untouched? Because when you do matrix multiplication there, it's still just an identity when it comes to the first row, right? So I didn't mess with the first row. I also didn't mess with the last row, but we're going to mess with that one soon. So let's wait. What did I do to the second row? First of all, I kept the 1 on the diagonal. So it's clear that these numbers are going to be 2, 5, 8. But I'm also subtracting -2 of the first row. You have to go through it to just see that every time you multiply -2 plus 1 plus 0. -2 times that plus 1 times that. So you should see I'm doing -2 times that plus 1 times that on all of these. So I'm really doing Gaussian elimination here. -2 times this, that's -3. -14, that's -6. All right? So this is basically the essence of being able to write Gaussian elimination as factorization. That these operations are matrix-matrix products. What do you think I'm going to put there? -3, exactly. I'm going to do this in one sweep. You don't have to. You could say that this is the first step, but it's so easy to just do them all at once because it's completely independent that I now want to do the same thing to put a 0 there, right? And you could again just do the matrix-matrix multiplication to convince yourself, I'm not going to touch this one. And of course, this is a lower triangular matrix, right? So convince yourself that this is one step of Gaussian elimination, zeroing out everything below the first pivot. And I can do the calculations. That's a 6 minus 3 times that, that's -6. 9 minus 3 times that, 21, that's 12, I think. Yeah, good. All right, so this is probably the first ingredient. And let me call this something. Let me call this something I multiply from the left the first time, m. The first m from the left. And let me call the result A2. It's a new A. All right? And then we do it again, and then we're done. So now you take your new A. Of course, you don't write it like this, but you could. I'm just copying it. 0 minus 6 minus 12. This was this new A we had, A2. We want to keep on going to do another step of Gaussian elimination that we, of course, are going to call A3. And this, you can probably guess, I'm going to call M2. I want to multiply by some new thing that does another step of Gaussian elimination. And we started with identity here, which makes a lot of sense. It's easy now. What the operation I want to do is subtract 2 times row 2 from row 3, right? So you can convince yourself where this minus 2 is going. But let's just say that clearly these are all 0, right? Because I'm not touching row 1 and 2. Clearly this is 0 because I'm not subtracting anything times row 1 this time from row 3. I'm subtracting something times row 2, namely minus 2 times row 2 from row 3. Goes exactly there, and then result is this. 0 minus 3 minus 6, and now we get a 0. It turns out we got one more 0. It doesn't matter. In fact, it might have mattered. Since I'm not pivoting, I could not have continued, but I got away with it. All right, let's collect our thoughts, because it's not at all clear still that we've done this. Let me erase this, or let me hide this, and just show what we have. We've basically multiplied by m's from the left. So what we did was that we said that you multiply A by an M1, and then I took the result, I call that A2, right? And multiplied by M2. And then I was done. That led to what I call A3. And let me just now give it a name. That is upper triangular, right? Because of Gaussian elimination. So this is going to be my U. All right, so there are many unclear things here. One is the L there. There's an M here, but there's not an L there. So somehow we're going to have to invert the M and bring it to the right and see that it's an L. And also we're multiplying these together. It's not clear what that's going to do, right? So let's look into that. But formally we can still just write that A will be the inverse of this matrix. Of course, you're not going to calculate. We're going to tell you exactly what it is. We can, if we want to write it like this, it's M1 inverse M2 inverse applied on U. All right? And the hope here is that this, or if this is working, this better be an L, right? Otherwise, I messed it up. Okay, and let me just tell you that there's a little bit of when we teach this to the grad students in 221, if you're interested, we call it, I know a very famous book, we call it 3 strokes of luck. Namely that this whole process, I mean, it's not luck because there are reasons it has to work out, but it's not at all clear that these things would work out. That taking the inverses of these lower triangular matrices of this form and multiplying them together like this doesn't completely mess up everything. Remember, matrix is a pretty complicated operation. Why is that a lower triangular matrix? It's not clear at all. So they call that sometimes stroke of luck. But let me give you the punchline here. At the end, it turns out that this L is really just ones. And with plus signs, here come the multipliers. Exactly those numbers that we used before. And multipliers we define without the signs. So I know, when you know this, and this is how you'll solve most of your homework problems on this, that you just know this. And we can prove it, but we're not going to really go through it. But this is the stroke of luck, that this L, all that product of the inverses, is really just an identity matrix with all the multipliers that you used in Gaussian elimination below the 1. So you all see that this is kind of nice, because doing this is exactly Gaussian elimination. Just recording the things you multiplied by, and the end result is U. So just to finish this example up, I'm kind of done. let me put it here. I just claim then that if this is true, A is equal to LU, which is 1, 0, 0. Well, let's write A as well so we can confirm it. A was 1, 2, 3, 4, 5, 6, 7, 8, 9. And that is equal to an L, which is 1, 1, 1, 2, 3, 2, times a U, which was 1, 4, 7, 0, minus 3, minus 6, 0, 0, 0. And you can, of course, confirm that that's how it can be done, but for now, we're just saying that this is what's going on. So kind of remarkable. Doing this, if we were to, we're going to motivate this now. But in practice, when you do it, as I said, you just do your 3. Remember, there were 3 operations for Gaussian elimination here. I put a 0 there, a there, a there, right? And they had 3 multipliers. I subtracted 2 times row 1. I subtracted 3 times row 1. I subtracted 2 times row 2. Those numbers go here, and you're done. So doing an LU factorization is easy in that sense. Let me just show you how these, if you want to indicate a little bit the magic that happened here without the proof, you can actually, the way I'm going to do it, you can almost see the proof coming. But let's just look at one of them. So I claim that you have this matrix in the left-hand side, right? This is what we called M1. M parentheses 1, right? That was that first matrix we multiplied from the left with minus 2s and minus 3. Now the magic is that its inverse is the same, but with plus signs. I claim that this is the inverse of M1. Sorry about the notation here. M1, big bracket, inverse, right? If I claim that something is an inverse, how do you test it? You just multiply. And you can kind of, if you want to see what's happening, clearly row number 1 is not going to do anything interesting. But if you look at row 2, you get a minus 2 times 1, and then you get plus 2 times 1. So that is a 0. And that's going to happen all the way down. Right? Now, 2, 2 has stuff here, but it's multiplied by 0, so it kind of works out. You might want to do this by hand just to see that this is coming out, which is, of course, the property of an inverse, right? And when you've done that, I think it would be a very small step to convince yourself that this is always true. In fact, a matrix that is an identity and a bunch of number below one of the ones has an inverse that is exactly the same thing but reversing those signs. So it's a property you can show easily. I'm just not going to do it because it needs notation. I don't like notation. But a simple example with numbers like this could convince you of that. Of course, that also shows another one. I'm going to write it out so we have it. The other one was this M2, which was 1, 0, 0, 0, 1, 0. And then we put the minus 2 there. And I, of course, claim that if you do the same thing of reversing the sign, you get the inverse of that matrix. So this is M2 inverse. And you can confirm that that's also equal to identity. And in fact, after you've done this, as I said, you could generalize to the n by n case with anything below the ones, and you see that this is the case. OK? I'm not fully done because I had to multiply them. Remember, I erased it, but I had here before that L is really M1 inverse times M2 inverse. So the second stroke of luck is that, so we have the inverses, but the second stroke of luck is that you multiply these things together, and they just combine nicely up to just align all the numbers into these slots here. And again, I'm just going to show it by an example. So you take this first inverse that looked like that from over there, and then you take this guy, and when you do this and do the matrix, you can convince yourself that clearly the first column here is not going to be messed up because of the zeros there. But maybe it's not so trivial to see that this 2 there is not getting messed up. It will end up exactly there. But it's just matrix-matrix multiplication. So that's it. I hope you're fine with that compromise of convincing your guys that it works. So the end result is so easy. You remember how to do it. But I also like you to just see that it's not a lot of magic. It might be luck, but it's not magic. Proving it is just knowing your matrix-matrix multiplication. And in words, what it all means is that simply subtracting rows from other rows by multiples is really just matrix-matrix multiplication. Let's see. I have some notation for the more general case. Let's bring it up. All right. Here's the general MK. Just generalizing. Remember, the M's were identities with multipliers with a minus sign below one of the i's, the pivot element, right? We can write that like this. This is identity matrix. And below one of the pivot elements, I put n minus k numbers. I put minus signs because the multiplier is defined to be really, if this is a, the multiplier is that divided by that. So the way you remember the sign there is that you subtract the multiple times a row. If you want to add, it's, of course, there's a sign difference in definition. But this is it. So that's sometimes called a Gaussian transformation matrix, right? Because it's doing a step of Gaussian elimination. And then the next step was to convince yourself that you do this and you insert these zeros here, right? And then you keep on going, and that's just multiplying by another matrix. And you keep on going yn minus 1 times. Actually, this mimics you remember the for loop, the outer for loop in my Gauss elim code. It only went to n minus 1, right? Because there is no last step. When the pivot element is here, you're done. So there is no nth step in Gaussian elimination. There are n minus 1 steps. So that will lead to n minus 1 of these M matrices that multiply in this order, A, like that, and it produces this matrix. And if you want to get into notation, clearly you see the A subscript here. It's really just matrix elements, right? But the superscripts here are supposed to tell you where they come from. And the parenthesis 1, you remember I said that was really A1, right? So it's another way to say that the first row we don't touch. The second row is not, of course, the original A. So we put a 2 on it. It comes from the second iteration. And keep on going, right? It's just notation. But it's clear that this is the first step to realize that the nth A, and this is, by the way, the U. So the nth A is, then you're done. Here came the first step of magic, that when you take this matrix M and invert it, you get an L. And so far, we're not at the big L. We're just at one of the sub-Ls. I never gave it a name. But each of these inverses you could call L1, L2, etc., right? Obvious notation. And the stroke of luck was that I indicated here that you really just reverse the signs of these, not of the matrix. It's not minus L, because the ones are still ones. I'm just reversing the signs of these M's, and that is the M inverse. And, well, the second stroke of luck is not pointed out here, but it comes down here. That then you move everything to the right, and you get all these L's multiplying. And it turns out that they actually do cancel out to A's. This is halfway to the proof that it works out. It's just saying that if you define this L, and you see that that's the inverse, the fact that they came together like I showed here, so this property, the fact that you had a bunch of these with just one column being non-zero, and then they multiply together and going nicely like that, is essentially proven in the last lines here. Because you claim that you define these matrices L to be this M inverse. You show that, but then you multiply them together in the right order, and you see that they will pairwise just eat each other until you get A back. So it's fairly easy to show that. That's the whole method. Here's the summary. As a theorem, if Gaussian elimination can be performed without row exchanges, that's a big if, because zeros might show up, right? Then you can factor A as a lower triangular L and an upper triangular U, as A equals LU. These M's are really just the multipliers showing up. Again, notation, because there are lots of multipliers. And you get an upper triangular U coming out of it, and a lower triangular M with 1s on the diagonal coming out of it. All right? I have, just as a little example, for MATLAB, let's make a little demo. So I call it LU demo, and I'll tell you what I do. I take a matrix A, maybe I'll just, so we can look at it. There it is. So it's a little bigger than I wanted to do on the blackboard. So you can see the process. I'm going to need to create these M matrices, and I think you can see that creating one of these M guys would take forever. It's 1, 0, 0. With a 4x4, it would take a long time. So why not write a little utility called make M, such that I can say make M 4x4, and you want to put these numbers at the appropriate place and create that matrix. Now, just in terms of programming, look at how did you think maybe this was not a good way to design it. How did it know where to put those numbers? Yeah. Yeah, so that's, I'm not saying that's a good programming style. But clearly, I designed it as short as I could. I want to later on create a matrix where I put zeros, where I put non-zeros below some other one, right? I think it really should be a parameter here saying, where do you want it to go? But I observed, like you said, that from the number of elements I gave and the size of the matrix, that is given. So, Anyway, this is just a way to create those. If you want to learn MATLAB, you look at that matrix, and you see that you create an identity matrix. You figure out where you want it to go, and you put it there. Okay? It's a stupid do-nothing type method. It's not really calculating anything, but it's creating this for us. All right, let's go back to LU demo. So we have an A, and the first step is that we identify the multipliers. And what are the multipliers? I went a little too fast when I did them. I would rather say that the multipliers are 4, 8, 6 divided by 2, right? Can you see where all those numbers coming from? So remember I said that this first multiplier was 2. 2 divided by 1. That's what you have to subtract this row from this to 0 out, right? 3 divided by 1 was this guy. In general, all these guys, whatever they are, divided by the pivot element. That is the multiplier. So the multipliers are these numbers here. Now I'm creating M's, which are by definition, I know the signs could be confused. You could rederive this yourself, renaming and changing the signs. But I'm going to use it such that I want minus signs there. And then I get that matrix, okay? And what I claimed from all of this, and now I'm going to do it on the computer, is that if you take M1 and multiply A from the left, you will put zeros there. You will not touch the first row. You will, of course, mess up everything else, but you will introduce zeros here by design. Okay? So if you actually wanted to create a computer code for this, you would just put A of, and you could take those numbers from A, right? I'm not doing that. I'm just writing them for pedagogical reasons. And this is, of course, A of 1, 1. Or I guess in general it would be I, I if there was a for loop. Anyway, so now we define another M. And what is the M going to be now? Now I want to subtract, I want to make this 0, right? By subtracting a multiple of this row, and that multiple is going to be minus 3. In general, it's 3, 4 divided by the pivot 1, and I want to multiply by minus. You can see my script magically putting those numbers at the right spot. That's where they have to go, such that M2 times M1 times A now zeroes out them as well. All right? And for the last one, we need an M3 that is 4, and it's going to take that 2, divide by 2, and put a minus sign. Or maybe it's easy. I'm just doing it in general case, but it's okay. I want to subtract this row from this row to do Gaussian elimination. So there's my M3, pretty obvious. And of course, the end conclusion here now is that if you do all these together, you've done Gaussian elimination. This is what we call U as an upper triangular. And it remains to be seen what L is. Of course, we know what L is. You're just supposed to put all those numbers that you had that I already traded, right? Without the minus signs, together like this, right? But let's just, again, see that it makes sense. So if you look at M1 and the inverse of M1, I claim that the the way to invert a matrix like this is to just replace the sign. And that's true for all of these guys. So this was that first stroke of luck. That you can invert the left matrix here by just changing the sign of everything below the diagonal. Okay, what else am I doing here? Well, the next one was that if you now multiply all of those together, they actually don't mess each other up. They will just nicely put all those 2, 4, 3, 3, 4, and 1s below the diagonal with a new plus sign. This is what we call L. And just to confirm that A is equal to L times U. All right? That's the demo. If you now wanted to solve this, as I said, you first have to solve the system Ly equals B, which is easy because it's triangular, but it's a back solve. We don't have code for it. It's actually a forward solve because you start on the top, at the top. When that is done, you have to take this U, and that's the usual back solve, just like in Gaussian elimination. But when I've done this work, I can just sit on my L and U here, and you could feed me B1, B2, whatever right-hand sides, which is very common in application. Signal processing people, you have a real-time device somewhere, and data is coming in from some measurement thing wherever, right? And every time you get data, you want to invert it, like you want to solve AX equals B. Clearly, you want to do some pre-computations like this. All right, one big thing I have not covered is row changes, which I said is critical, so we better handle it. And I'm not going to make too much a deal of it, but guess what? It can also be written as matrix-matrix multiplication. You might have heard in linear algebra classes what a permutation matrix is. If you give me a perturbation of the numbers 1, 2, 3 up to n, you can create a corresponding permutation matrix by putting a 1 at the column, in detail here, at the column given by the ith number, you put a 1. So it's only only a single 1 per row, and it's of course just a permutation of the columns of the identity matrix. If you multiply this P by A from the left, you will permute the corresponding rows. And actually, if you wanted to permute, this notation here shows you that what used to be A1, 1 is now, it switched row with row K1, so now it's a K1, 1. And the same for the entire row. The same all the way through. Let me give a little demo of this. I didn't put it in the code, but of course I have a make P. Okay? So I have a make P. Let's take the matrix A we had here. What would the first step be, actually, before I do Gaussian elimination? What would I do there first step? In fact, I would not do it if I don't want to do partial pivoting, which I should. I did it wrong before. Because remember, you always got to make sure that the largest number is at the pivot element. I used 2. This was my pivot element for the first step. That's not OK. It has to be the largest number below it, including it. But that's 8, right? So the very first step is to switch row 1 and 3. And all I'm going to say now is that can be done by multiplying by a P. And the reason is, I mean, in a computer, you might not do it this way. You probably don't do it this way. But we want to be able to write things as matrix multiplications like this. So I'm claiming that I can create a P that flips rows 1 and 3. And it just looks like that. Okay? And if you multiply A by this P1 from the left, you will take the rows 1 and 3 and flip them. Okay? And it's, of course, no magic, except that I did it with a matrix-matrix multiplication. Now, then you keep on going, and you do an L. And there's actually, this is the third stroke of luck, and it's not covered in the book, and you don't have to know that part. But if you think about it, I will do more P's, right? And because I'm going to have to keep on doing P's, because this problem shows up. Every time you do it, you have to choose the largest pivot element. But the problem is that they are not coming together. Because after this, now I will multiply by an M from the left, right? In fact, what I call M1. Then I multiply by another P, then an M, etc. So the fact that all this still works out is not clear. But it does. And to summarize it with a slide, well, first of all, the P inverse is very easy to do. By many reasons, you can convince yourself that it's really just a transpose of P. Okay? In this case, of course, they are identical. Flipping 2 rows is the same as the inverse is flipping them back. But if you have a more complicated permutation, you have to do the transpose. Here's the end result. This is often called the PA. You often put the P on the left and write this as PA equals LU. But you can, of course, move over the P. You can use the fact that it's just a transpose to say that this is the LU factorization with permutations. And all that happened is that a P came out. And it's not clear at all that all those P's that were interlaced with all those M's could actually be taken out just like a P. But the way to remember it is, of course, that all you do is that you pre-scale all the rows of A, and then it's just LU. So I didn't give you a code for this, but I thought I could show you in MATLAB because this is good to know. Here's our matrix A. In MATLAB, they do have a command for all of this, and it's called, big surprise, LU. Okay? And you'll see that it's quite different result from the one we just did because of the permutations. So apparently, after everything was said and done, this is the permutation it decided to do. Okay? And after doing so, it got an L out of it, and it got the U out of it. You see that it put the 8. The first thing it did was to put the 8 up here, right? But then it kept on doing other things. Remember one observation I said about partial pivoting? If you always put the largest element up here, all those multipliers, 2 divided by 1, 3 divided by 1, are going to be less than 1. Maybe negative. Why? Because this is the largest element of them all in absolutes. And indeed, you can see that our L here has no 1s, nothing greater than 1. That's a nice property. This is what gives these nice numerical properties that we haven't really discussed. I just mentioned that I did show the 2 by 2 where things could go bad if you didn't do this. Apart from that, it's not a big surprise. We could use the code that I had before. If we go back here and cheat, this is the demo I did before. If I just magically say that I know this permutation matrix, and just cheat and do, oh, I wrote the code wrong. All right, let's do it anyway. So let's do it by hand. So if we do A is equal to P, so magically we just know that this is the right order. Let me now do matrix multiplication again. So you do M1 was, of course, and let me write it in the more general way. It was, of course, the 2 to 4th column, comma 1 divided by A11. All right? So now I'm doing it again with a more general framework. The 3 multipliers at step 1 is going to be A of 21, 31, 41 divided by A11. And a minus sign, because that's what I wanted. OK? And then you're doing M1 times A. And this is what we called A2. And it's zeroed out as before. Now I want to create an M2 that is going to be this A2, and it's now elements that. You can think about that if you want to. But that gives you something such that when you do M2 times A2, you now zeroed out those. And the last one is M3 is make M4, and it's going to be minus A3, 4,3. It's only one number, like that. And it has the property that A4 is M3 times A3. And now you're done. In fact, this is U. All right? And now it's identical to MATLAB. So the only difference is that they figured out the permutation. You could do it, if you did it, you would get the same result, but I didn't code it up. All right, is that confusing? Are you guys shocked? It's kind of nice. Let me tell you one warning sign just about MATLAB. Nobody knows this. Even if they took a course like this in undergrad, all senior people working with it, they are saying, I don't need to permute. So they do this all the time. Okay? And MATLAB, of course, they're responsible, and they want to be, they want to tend to the needs of these people. They feel that they know something, but they're wrong. So guess what MATLAB did? They will not produce bad results. You cannot do LU without permutations. But still, people want to do it. They do this. So they did a really ugly. It's almost immoral what they did. They permute L. They don't give you an L. They give you a new matrix that is. Oh, I messed up A. Let's go back to my original A. They messed up L. This is not an L. This is a U, but this is really a permuted L. And the reason they did it is just so they kind of take care of it for you. I mean, you don't get an L out. You thought you would, but you don't. But likely people don't look at it even. They just use it as if it was an L, which means that they can do a quick back solve. And it actually works out. It's a little weird. They kind of take care of people. I think they should return an error message saying, look, I refuse to do LU without permutation. Please do L, U, P equals LU of A. But they thought this was a good solution. It's kind of funny because you'll see people say, oh, those permutations are not important. I do it all the time in MATLAB, and I'm fine. And I'm like, no, you don't. They take care of it for you. But that's OK. Anyway, MATLAB is a little iffy sometimes. They do a little too much under the hood. All right, have fun with that. I'll see you guys on Thursday or office hours.